Hi everyone, welcome to the Methods 3-4 lecture. My name is Manjot and I'll be taking the lecture today. Just before we begin, I'd like to talk a little bit about ATAR Notes. So since 2007, ATAR Notes have been offering heaps of free resources to make sure that students like yourself can thrive in their studies. And we've also offered lectures like the ones today since 2015. And these all align with our mission to help students as much as possible so that they have the best chance of succeeding in their studies. We also offer a bunch of free resources to help students, such as our study notes, lectures, such as the one that you're watching today, discussions, videos, newsletters, ATAR calculators, articles, and heaps more. So if you're interested in how to use these resources as well as where you can access them, please check out the info doc under the resources section of the lecture page. And if you have any questions, please pop it through into the Q&A, and I will be answering those questions as they come up. Okay, so let's get started with today's lecture. So today's lecture will be mostly just revision of all the content that you've learned throughout the year, just as a form of revision for the end of your exam. Obviously, we won't be going through absolutely everything, but we will try to get through as much as we can of the course content. So just to briefly introduce myself, my name is Manjot Bulla, and I graduated recently with an ATAR of 99.8, and I'm currently studying a Bachelor of Biomedical Science at Monash. And I tutor maths and science at TuteSmart, and the subjects that I did throughout VCE were chemistry, maths methods, specialist maths, English, biology, and further maths. And today what we'll be covering is functions, calculus, and probability. So the structure of the lecture is a little bit different this time around, so there will be no designated breaks, so pause whenever you need. And we'll also be using the Q&A software, so if you have any questions, please pop them through into the chat, and I'll be monitoring the chat, so I'll be answering the questions as they come up. Okay, so for the first part of the lesson, we'll be focusing on functions and relations, then we'll be focusing on transformations, logarithms, exponentials, circular functions, and then we'll move on to more calculus, so differentiation and applications, integration and applications, probability, and then lastly, we'll be moving to binomial distribution and the normal distribution. Okay, let's move on with today's lecture. So to get started, we'll be looking at functions and algebra. So we'll be looking at the different types of functions and relations, and also the specific notations of defining functions. Then we'll be looking at transformations, and also looking at logarithms and exponentials, and lastly for looking at circular functions. So this lesson will be more so focused on the exam side of things. So what sort of things you need to look out for in terms of doing well for the exam. And for functions, I would say the most important thing, if not for the entire maths methods course, is notation. So getting your notation right, knowing how to basically define certain things in terms of their notation, as opposed to other aspects of the course. So we'll be going over how we use notation for different functions and looking at how to get full marks for just these simple things that not really maths, but just in terms of how to actually, how to show you're working out essentially, and using the correct notation to show that working out to your examiners. So for trig and log functions, remember to always have brackets. So even if it's just sin x or sine x, make sure you have brackets around it. So a lot of people, or a lot of students end up just writing sine x. So this is completely wrong. You need to have log x. Similarly, if you have something like log, remember to have log, then the base underneath, and then the bracket. Really, really important when we are notating to have this correct notation. For every brackets that you use, make sure there are no lonely brackets. So don't just have one bracket on one side and no bracket on the other side. So make sure we have 2 brackets. And that's specifically important for stuff like, functions, for example, or, calculus. We need a lot of brackets sometimes. So thinking of brackets, it's sort of thinking like the integral symbol. So if we have the integral symbol, we need to follow it by a dx. That's another thing that we'll come back to in the calculus section. But notation, as you can see, is super, super important in terms of getting, the full marks that you possibly can. For function notation, always leave, or not just functions, but just, across the exam, leave your answers in exact form unless the question actually specifies the need for a decimal answer. Really important here, so stuff like, pi, roots, square roots, need to be left in this form and not in decimals unless specified so. Another thing, just in terms of using your calculator for exam 2, leave your calculator in radians. There are not going to be as many questions that require degrees. If there are, it will be highly sort of explicit that they require degrees, and then you can switch. But leave your calculator in radians mode. Otherwise, your calculator just goes bonkers. To be honest, you're gonna get really wrong values, and you're gonna be like, why am I getting these values? In the exam, sometimes it's not that obvious. You might just get a really weird value, and you might be like, yep, that's the answer. And your calculator might be in radians, specifically when you're doing circular functions, but also like in other, like for example, calculus. If you don't have your calculator in radians mode, it gives you weird derivatives and antiderivatives. So just overall, really important to leave your calculator in radians mode. Also, another thing, most people don't really do this, but if you are, you're not allowed to put any tech jargon. So for example, if you're trying to solve something, don't write solve and then whatever the function is, or derive and then whatever the function is. Use mathematical notation. This is something only restricted for your calculator. Your examiners don't need to see how you've done it, especially on your calculator. They don't need to know how you've done it. They only need to see you're working out. So whatever this thing is, whatever you're trying to solve. Okay, so just some other notation. So if your function is y, then we use dy dx when we're deriving it. If your function is f of x, then we use f dash x. And if you're just differentiating a random expression, which is not an equation, then we use ddx, and then we put in brackets what we are basically deriving. So what's the expression that we're deriving? Really important. It really does make a difference. Well, in the grand scheme of things, it doesn't really matter that much, but overall, in terms of your working out, this would actually be really important. And also letters as well. So if it's f of x, we use f dash x. If it's g of x, then we use g dash x. Just overall, notation for calculus is going to be super duper important in terms of getting to the final answer. And also just making it clear for your examiners what you're actually doing. Again, make sure when we're writing logs, we have a base. So base means it sort of needs to be like a subscript, not in line with the rest of the expression. For example, here, we have the e in line with the rest of the expression, which is not allowed. We need to have it below as a base. Also, ln x is the same as log x, but not log 10x. Another small sort of thing that a lot of students don't understand, ln x actually means log ex. So you can write it in the exam as ln x as opposed to log ex. But if you're confused, just continue using log ex. But in your calculator, usually your answer will be given in this form. So just remember it's log ex, not log 10x. Another thing is when you have a function, you can refer it to as a function in the entire question. So let's just say we have an exam 2 question where in question 1, they define a particular function. You don't have to write down the function again and again and again in every single part of that question. You can refer to it as f of x or g of x or h of x, whatever it is, throughout the entire question. Really important to make sure that we're not wasting time on things that literally don't need that time. We should be spending more time actually doing the questions as opposed to fixing our notation, making sure that the examiners know what f of x is. So if you just write f of x is equal to 2, for example, so if you're solving and you just write f of x is equal to 2, they know that you're solving whatever f of x is equals to 2. You don't have to write, if the function is like sine x, you don't have to write sine x is equals to 2 every single time. I mean, for sine x, it's a small function, doesn't really matter, but if you have like a really long function, especially with like fractions and stuff, then it gets a little bit more complicated. So try to use f of x if you've already defined it. Another sort of thing that a lot of students get confused with is inverse functions. So we'll come back to that in a few slides later, but f negative 1 of x is not the same as the reciprocal. So this is the reciprocal. It's f to the power of negative 1. It's certainly not f to the power of negative 1. That would be f to the power of negative 1. This is this. But when it's f negative 1, that actually means inverse. So we're finding the inverse function, which we'll have a look at a few slides across. Another thing, 1 over x plus y is not the same as 1 over x plus 1 over y. They're completely different things. A lot of people get confused by this, because if we have x plus y over, let's say 2, this is equal to x over 2 plus y over 2. So this is where a lot of people, students get confused from. So when it's on the top, you can do that. But when it's at the denominator, that's actually not allowed. So for example, what I've done here, x over 2 plus y over 2 is allowed. So this is equal to this, but this is not equal to this. So when it's in the denominator, you can't split it like that. So just really important to make sure, especially when we look at like hyperbolic functions and when we're trying to solve them. A lot of students end up making this mistake. When you're manipulating expressions, so when you're doing some form of algebra, first of all, I would say use your calculator when you can. But if it's exam 1, the things that you have to be most careful of is fractions, negatives, square roots, and inequalities. This is what's going to mess up everyone's working out, especially when you're trying to work really fast and really quickly through the exam. You're going to mess up these sort of things. Everyone always messes up negatives, for example. So you're really likely to make these mistakes in the exam. So when you're doing practice, really try to be conscious of, how you're using these negatives, how you're using these fractions, so to avoid making any mistakes. And if you know that you're going to make this mistake, write it somewhere. For example, if you're allowed a summary book in exam 2, write it in your summary book, for example, and I'll go through that at the end of the lesson, but make sure you're really conscious of the mistakes that you're making. And these are the mistakes which every students are going to make when they're manipulating algebraic expressions. So these are the ones that you have to be extra careful of. Okay, so now we'll move on to function notation. So function notation is how we denote a function. So this is full function notation. So this involves, first of all, the naming of the function, so what the function is called, usually depicted by a letter. Then you have the domain of the function. So I'm pretty sure everyone would be familiar with what a domain means. It's just the possible values that a function can lie within. And then we have the codomain, which is always going to be R for maths methods. And then comma, and then what the actual rule of the function is. So this is the entire function notation. So when you're being asked to give your answer in function notation, or what the function is, something like define the function or something like that, you have to give your answer in function notation just like this. So basic understanding is required for the exam. So especially in exam 1, they have a lot of questions involving inverse functions where they ask you to give your answer in function notation. So be careful when labeling the function name and dependent variable, and look at marks to see if domain is required. So I would personally just always give domain when asked to, when I'm asked a question, which although some questions might not explicitly ask to give your answer in function notation, but if a question says define the function, define whatever f-1 of x is, for example, I would just give it in this form with my domain included. Sometimes you can leave it as just the rule. I personally just wouldn't risk it. Okay, so now we'll look at implied and maximal domain. So a maximal and implied domain is essentially just the maximal domain is essentially just what's the maximal domain that a function can be defined for without having any sort of algebraic discrepancies, for example. And implied is just a domain that's applied for a certain function. Maximal domain can be restricted for certain functions, whereas the implied is just, you're not limiting the domain. It's just what it is for whatever the function may be. So here are a few examples that you may have to work out the domain for, or the implied domain for. So if you have something like a over dx plus gx, we know that the d of x, or whatever's in the denominator, can't be equal to 0. So in that case, the domain is actually going to be, so what we do when we are trying to work out the domain, we let d of x is equal to 0, and then we work out what values that's going to be. So that's the values that our d of x can't, or our x can't take. So let's say we had x minus 2 in the denominator, x minus 2. We know that can't equal to 0. And then if we rearrange this, we'll soon realize that x can't be equal to 2. So that is our domain. Another thing, for example, square roots come up really often. So square roots, we can't have a negative number inside a root. So therefore, the numbers inside, or x, has to be always greater than or equal to 0 when you have a square root. And when you have a square root in the denominator, which might come on the exam, but still it's very rare. There's two things that you need to know. First of all, it can't be equal to 0, or it has to be greater than or equal to 0, and it also can't be equal to 0. So therefore, it has to be greater than 0 in the square root, if the square root's in the denominator. So it's just knowing the properties of different functions that's really important when you're working out an implied or maximal domain. So oftentimes you will be required to know, what these functions are. And then when you're working out the domain, you have to just use the properties of these functions. So for example, a over dx, we know that something in the denominator can never be equal to 0. Something inside a square root can never be less than 0. And using those properties to then work out what are the values that my x cannot be, or what are my values that x can be, which is essentially the implied or the maximal domain. Okay, so here is just a quick example of where this might be handy. So if we have something like solve root x is equal to 2 minus x for x, well, what do we know about this? Well, we know that, this one's just a basic solving question, but we'll come back to the domain part. So what do we know about this? Well, we know that, first step is usually when we're solving this, is to actually probably square this number over here, because that way we can eliminate the square root as shown in the first step. And then what we can do is just expand the expression on the right to give us x is equal to 4 minus 4x minus x squared. And then this is just a normal quadratic equation. We can move the x to the right hand side, and then we can factorize, and then using the null factor law we can solve. But something that you will notice is root x might not be equal to all the values. It has a certain domain. So the domain that we need to work out is root, so first of all, we know that root x must be greater than or equal to 0. Right? So we know that root x, whatever's inside the root x, has to be greater than 0. And since whatever root x, whatever we put inside root x is going to be greater than 0, whatever the answer is going to be also has to be greater than or equal to 0. So that's because, let's say we have root x, and let's say we put, 2 inside, this value is also going to be greater than or equal to 0. So therefore 2 minus x is also greater than or equal to 0. So therefore our domain is actually going to be between 0 or 2, because if we rearrange this, we will get, so again, just solving a basic inequality here. We're going to get x is less than or equal to 2. And we know that x must be greater than or equal to 0 from this part of the function. So therefore, our domain is actually 0 to 2. So therefore, we can actually eliminate 4 as a potential answer option. So I hope that makes sense. Let me know if you have any questions. Okay, so now we'll look at sum and product functions. So this is essentially when we have multiple functions and we're either adding them or multiplying them together. But what we need to know importantly is their domain and how multiplying or adding a function will affect their domain. So the domain of a function, when you add them or multiply them, is essentially just going to be the intersection of the two functions that you're multiplying or adding together. And that's because, let's just say you have a function f of x defined from 2 to 4, for example. And you have g of x, let's just say, defined for 0 to 3. Now if we just draw a quick number line, we have 0, 1, 2, 3, 4. So function f is defined for, so it can only take values between 0, 2, and 4. Whereas g can only take values from 0 to 3. So if we add them up together, g can't be, g cannot even take values less than 0 or greater than 3. So if we sub in, for example, 4, g is actually going to be undefined at that point. So therefore, when we're working out the domain, when we're multiplying or adding function, it's just going to be the intersection of these 2 points. So where are the domains overlapping each other? Which in this case is going to be 2 and 3. So that's, therefore, the domain of this function is going to be 2 to 3. So I would always sketch this sort of number line if it's possible, and then use that to work out the domain. Okay. So now we'll move on to composite functions. So these are what confuse literally every maths method student. So essentially when we are doing a composite function, what we're doing essentially is we're putting one function inside of another function. And let's just say we have, just draw it out quickly. Let's just say we have a function like this that goes from 0 to, let's say it's a normal linear function. It goes from 0 to 2 and then to 4. So this function is always fine. So let's say this is g of x. So h of x is actually g of x. So f of x is h of x is actually f of x with g of x inside of it. But f of x can only be defined for the domain, for the range of g, because for g, it can only be defined, or the values that it produces is going to be between 0 and 4. So therefore, the domain of the f must now be 0 to 4 as well, because otherwise, if we left just say sub in, we can't really sub in a value greater than this. Let's just say we have, g being 3. We can't have a value for 3 because g cannot be defined for anything greater than 3. So therefore, the domain of the function is just going to be the domain of the composite function is just equal to the domain of the inside function, g of x. However, if we're trying to work out the range or or if we're trying to work out if a composite function is defined, it can only be defined if the range of g is a subset of the domain of f. So let's just say now we have a new function, which is f, which is defined for, let's just say, another linear function, but only defined for, let's say 5. Oh, that doesn't look like 5, but, oh yeah, 5 to about 10, for example. So when we sub in x, let's just say we sub in, 2 into x. And then we sub in 2, we get 4. But if we sub in 4 into f of x, we're not going to get a value because f is only defined from 5 to 10. So that's why it's really important to know that the range of g, so what are the y values that g is defined for, which we are then subbing into f, they are in a subset of the domain of f. If not, you will have to change your values and adjust for that. So here is an example. So we're trying to work out if f of g of x and g of f of x will exist. So we have f of x, which is x plus 1 squared, which is defined for all real values. And we have g of x, which is negative 3x plus 1, which is defined for 1 to 4. So I would always construct this table where I have f and g in domain and range. Now, if I'm trying to work out if f of g of x exists, the range of the inside function has to be a subset of the domain of the outside function. So what is the domain of g? Or what is the range of g? Well, it's negative 11 over 2. But can this fit inside the domain of f? Well, yes, it can. Because negative 11, 2 is a subset of all real numbers. So therefore, this does exist. So f of g of x will exist. But what about g of f of x? So what is the range of the inside function, f of x? That is 0 to infinity. But it does not fit inside 1 over 4. It can fit the other way around, so g of x, the domain of g fitting inside the range of f, but that's not what we're looking for. So therefore, g of f of x will actually not exist unless we are able to restrict the domain somehow. Restrict the domain of f of x, such as to restrict the range. So if we can restrict the range of f of x to be 1 to 4, or even less than that, then g of f of x can exist. But otherwise, it will not exist. Okay, so now we'll move on to inverse functions. So inverse functions are essentially where we have a function that is reflected in the line y equals x. But basically, simply speaking, we're swapping the x and y variables. So the x become the y become the x, essentially. And the notation here is f of inverse. So the inverse function of a particular function is just going to be that function to the power of negative 1. Well, not really the power of negative 1, it's just the way that we denote inverse, f of negative 1 or g of negative 1. And because we're actually swapping the x and y values, the domain and range is actually going to swap as well. So the domain of the inverse function is actually going to be the range of the original function, whereas the range of the inverse function is going to be the domain of the original function. So really important to notice that this might also, that this will happen. And when we're actually working out algebraically what an inverse function is going to be, we literally just swap x and y. That's all we do. And then we rearrange it to make, again, y the subject to find what f inverse of x is going to be. So VCA will require actually a systematic process for finding inverse functions, which we'll have a look at in this next slide. But often you're going to get inverse questions as multiple choice questions. So really important to just get this pat down, really especially talking about how the domain and range changes, and also what we're doing when we're finding an inverse function. So here is a quick example of a question you might get. So for f of x is equal to root x minus 2 plus 1, find f of inverse of x. So what we might do here, first of all, is notation again is really important. So first step would be to let y equals f of x. So we literally write let y equals f of x, because we're swapping x and y. So we don't want to swap f of x and y. That wouldn't make sense because f of x is y. So for inverse swap x and y, that is the next thing that we would write right next to y equals f of x. And then we actually swap x and y. So now the x is going to become y and the y is going to become x. And then we are going to rearrange or solve for y to get a new function. This time we should get a quadratic. And then we will apply any domain restrictions. So depending on what the range is of the original function, we might need to apply a domain restriction. But at the end, you should be able to write your answer in function notation like this. So f of inverse, then the domain, and obviously the codomain, and then what the rule is. Okay, so if we were to graphically represent inverse functions, they will look literally like this. You have the line y equals x, and you're literally just crossing it in that line. You're just crossing, or you're just sort of reflecting the two graphs across that line. So this was, the orange one was the original function, we're just crossing it. So if you look at the line y equals x, it should look like a mirror almost. So the value should be reflecting across that. A lot of the questions in the VCAT exam will give you, something like one of the graphs, and they might ask you to show or, select the one that most closely resembles the inverse function graph. Okay, so now we'll move on to the next part of the course, which is transformation. So transformations are really important because basically they help us graph, essentially. And being able to know what transformations are applied to certain functions, being able to describe the types of transformations and the order in which they occur is really important. So we need to memorize both the definitions and also the procedures for transforming functions. So here are the different types of transformations. We can either have a reflection, or we can have a dilation and a translation. So reflection, as the name suggests, is flipping a graph, either in the x-axis or the y-axis. So either going like this or going like this. Oh, if you can see that. Dilation is sort of like stretching or compacting the graph. So it's either going like this or coming back closer together. And then translation is literally just shifting the graph to the left or to the right. Okay, so now we'll look at dilations a little bit more closely. So when you're dilating by a factor k away from the x-axis, you can use the coordinate method. So everyone should be familiar with the coordinate method. If you're not, essentially we use this coordinate method to help us determine the transformation and then apply it to the original, function. So if our original coordinates are x, y, and we apply a dilation of factor k, we are actually going to affect the y values because we're dilating away from the x-axis. So just to quickly illustrate this. So if the original function is like this, and if we're dilating from the x-axis, what are we essentially doing? So we're moving it this way or like this. So we're stretching it or compacting it. So what is changing? The x values are remaining the same. So these two values will be the same. But what is changing? It's the y values that actually change. So that's why we do ky. Because the k is what the y values are going to be multiplied by. And then, if that's just the only transformation, you replace y with y over k in your actual equation, and then you can rearrange to solve for y, and then you will get your new equation. Or alternatively, you can do this. So if you have y equals f of x, to transform or dilate by a factor of k from the x-axis, we can just do y equals k f of x. Function notation is really great because you can do it on your CADs in like one step if you know how to use it properly. So I would probably have like a table with the different transformations and how to apply them. Both using the coordinate and also the function notation method. Then we have dilations from the y-axis. So this time we're actually changing the x values, because what we're going to do is if we apply it, we're actually going to stretch it away from the x-axis. So that's actually going to stretch like this. And when it stretches like this, what it's going to change is actually going to change the x values. And when the x values change, so when the x values change, that's why we have kx. And this time, when we are using function notation, you can do x over k. So f of x over k. So again, let me know if you have any questions, but transformation should be pretty straightforward. But yes, if you do have any questions, let me know. Next, we have reflections. So reflections, as the name suggests, excuse me, guys. So reflections will actually reflect the graph either in the x-axis or the y-axis, depending on where it's from. So if it's reflection in the x-axis, so this is the x-axis, it's going to reflect like this. But is the x values changing or the y values changing? Well, still, the y values are going to change. Originally they were positive, now they're going to become negative. X value is still the same. And similarly, if we have I'm going to use a different graph, but if we have a graph like this, if we're reflecting in the y-axis, we can reflect like this. It's just reflecting across. And when we're reflecting the graph, it's actually x values that are going to change at those particular points. So therefore, we replace it with negative x instead. Just like this. So that's essentially reflections. And now if we do translations, we can either vertical or horizontal, and we can either have them from the x or the y-axis. So depending on where you have the translations, they will either impact the y values or the x values. So if it's a translation, if it's a vertical, then it's going to affect the y values. If it's a horizontal, then it's going to affect the x values. And essentially, we're either shifting up or down or right and left. So, and this is how you can do the reflection, the translations using function notation. So if it's y minus k, I always use the coordinate method. It really just helps me know what's going on. So if it's a translation by k units in the positive direction of the y-axis, we are now going up. So y plus k. However, if it's a translation in the x-axis, we are now going left or right, depending on what that factor is. So that should be pretty straightforward for transformations. Now we'll quickly look at an example. So we have the function g of x, which has been shifted 3 units, left 3 units, then dilated by a factor of 2 from the y-axis. Okay, another thing that you really need to make sure of is usually transformations are always applied in this order. So dilations and reflections and translations, but VCAR always like to mix it up just to confuse students. So if that is the case, really make sure that you're applying one transformation, then the next, then the next. Okay, so in this case, we have the horizontal translation first of left 3 units. Then dilated by a factor of 2 from the y-axis. So a dilation next. So if g of x is equal to log e 3x minus 1, find f of x, the transformed function. So in this case, we can use either function notation or we can use the coordinate method. So I've used the function notation here. So first step, translating left 3 units. So it's actually going to be x plus 3 because if we use the coordinate method, we would need to sort of rearrange it and it comes to actually x plus 3. So this is actually indicated in this over here. So if it's positive, it shifts in the positive direction. If it's negative, it shifts in the negative direction. So if it's x plus, if it's shifted left 3 units, then we do x plus 3. We can apply that transformation first before applying the next transformation, or we can apply it in the same step. And then we have dilation. So dilation from the y-axis affects the x value. So we just divide by 2. So function notation is actually a little bit confusing sometimes. So it's, although it's a dilation factor of 2, we actually divide by 2. Yeah, so really important to, so if you're confused by this method, really do try and use the coordinate method. I always try to use that method. So if I had used the coordinate method, it would have looked something like this. So x, comma, y have transformed. So what is my first? So first I'm moving 3 units left. So it would just be x minus 3. And then dilation of a factor of 2 from the y-axis. So after this, it would be, just give me a second. It would be 2 y, sorry, why am I doing y? X minus 3. It's 2 brackets x minus 3 because I'm applying that transformation after. I'm applying the dilation after doing the translation. That's why it's brackets. Otherwise, it would just be 2x minus 3 just by itself. And then I need to actually convert this because I need to now sub it into the equation. So x dash, what is x dash equal to? So x dash is 2x minus 3. Now, what is x equal to? Because I'm subbing in x back into the equation. So x is going to be x dash over 2 plus 3. And what do you know? This is the same as this over here. So this is how we can derive, sorry, not that one. So that is how we can derive this in the brackets for using in function notation. So you can use coordinate methods first. I would personally recommend doing that to avoid making any mistakes. Okay, so now we'll move on to the Euler's constant and exponential functions. So the Euler's number is just a constant like pi. So it's just a number, a natural number. And it sort of looks like this. A really complicated sort of expression which we won't look at, and it's not required for the course. But it has some very special properties in terms of calculation and finance because it's a natural number. So this is what it looks like. We have the E, which represents the Euler's number, which is approximately 2.72. Another special property, which we'll come back to when we do calculus, is that E of x is actually a derivative of itself. So the gradient of the function is the same as the function itself. Very strange, but that's how it is. Okay, so here are some exponential laws, really useful in exam 1, where you'll get these, when you'll have to solve some complicated equations. So, the first law is the addition law, where if we're multiplying 2 exponentials which have the same base, we can just add their power and write it to the same base. Similarly, if we're dividing 2 exponential functions with the same base, we can just subtract the 2 numbers. If we already have an exponential and we're putting that to a power, we can now multiply the powers and write it to the same base, because this is essentially a to the power of m times a to the power of n times a to the power of m n times. So essentially we're just adding or multiplying m by n. And then another property that might be useful sometimes when you're solving is if you have a to the power of m, you can actually write that as e to the power of m log ea. Because you can write a to the power of m as e log e in brackets. And then when we come back to the log functions, you'll understand why the m can be moved in front. But really powerful sort of tool to solve complicated questions. Here is just a question that you're likely to get in an exam scenario. So solve 13 times 16, 16 to the power of 3x minus 1 plus 2 times 4 to the power of 3x is equal to 0. So essentially what we are doing in this case is, first step is to write everything to the power of 4. So 4 squared 3x minus 1 plus 2, 4 to the power of 3x. And then we just swap the powers. So 4 to the power of 3x comes inside, and then 2 goes outside. So essentially what we've established here is sort of a quadratic expression. So you can use a similar sort of properties as a quadratic function. So you can even, if you're confused with the 4 to the power of 3x, you can let this entire thing equal to a, and then you can solve it as a normal quadratic expression. So this will factorize to 4 to the power of 3x minus 1, 4 to the power of 3x plus 1 equals 0. And then we can use null factor law to solve. And eventually we will get something in log. So yeah, just a question that you're most likely to get in an exam scenario. And that's actually from here. So this will actually be undefined. So that won't give you a value. Okay, so now we'll look at logarithms quickly. So logarithms are essentially inverse functions of the exponent. So they have this form. So log b to the power of a is equal to a, because, just as an example, so if a to the power of e is equal to c, then log of the same base, so what's the base here? A. In brackets, we can put c. That's actually equal to the power. So log and exponentials are related in this way. So, when we're graphing exponential functions, they will have a vertical asymptote, because we know that log x can't take any values less than 0. Similarly, for exponential functions, I forgot to mention, is that they cannot actually take a value that is negative, a negative y value. So they will actually have an exponential, an asymptote at this as y equals 0. Just really important to know when you're sketching. But most of the time it will be done on CAD. So here are some of the log laws that might be useful in an exam. Again, in exam 1 especially. So if we have two logs with the same base and we're adding them together, we can multiply the numbers in the inside. If we are subtracting, however, we can divide the numbers with the number on the number that we are dividing from on the top. And another sort of really powerful rule is if we have a log and inside the brackets we have an exponential, we can actually move the power to the front, like this. And another rule that you need to know is the change of base law. So basically, when we want to change the base for whatever reason, maybe to simplify or, a variety of different reasons, we can actually change the base. So essentially what happens is whatever you want your new base to be, you write that in the denominator and in the numerator, and then the number in brackets is just going to be the number in this bracket at the top and the number and the base at the bottom bracket. So just having these log laws somewhere in your formula sheet, or when you're doing exam 1, just knowing these is really important, especially the first 3 really often come on the exam. This one does not come on the exam that often, but still really good to know, just in case. Okay, now we move on to the last type of function for maths methods. So that is circular functions. So circular functions are essentially derived from the basic functions sin x, cos x, and tan x. So basically, a circular function is essentially where, So first of all, I'll talk about what pi is. So pi is essentially 3.1415. So that is just, again, a natural number like e. And pi actually represents 180 degrees, or pi radians. So radians is the unit of measure that we use for circular functions. And radians actually measure the diameter of a circle. Sorry, not diameter, the arc length of a circle. So instead of measuring the angle between two values, it's actually going to measure this length over here. And that's why it involves pi. Okay, so here is the exact value table. Everyone should have this memorized by now. If you don't, you've still got like a month or so to memorize this, but try and get this memorized as soon as possible. Because you literally can't do some of the questions in exam 1 without knowing this exact value table. So just really important. I just want to point out that you have to memorize this. Okay, first we'll look at the sine and cosine functions and just their sort of basic sort of properties. So first of all, we have amplitude. So amplitude just represents the distance between, so circular functions, as you may know, repeat a certain number of units. So it's sort of like a wave repeats itself. A circular function is essentially just a wave, it repeats itself because of the unit circle, which we'll have a look at in a second. But essentially, amplitude is the distance from half of the graph to either the minimum or the maximum, or essentially it's just half of the distance from the maximum to the minimum of the graph. And for sine and cos, it's the same. For tan, it's a little bit different, which we'll come back to in a second. Tan doesn't really have an amplitude. Okay, next if we look at the period is essentially just how long or the distance between when the graph starts to repeat itself. So for example here, the graph is like this, and then after this point it's actually going to repeat itself because the circular functions actually repeat themselves from negative infinity to positive infinity, so they're indefinite. And the period just represents the length for which it repeats. A really common exam 1 or a multiple choice question, just Vika asking you what the amplitude and period is. Okay, so here are some symmetry properties of the circular functions, which is really important to know. I've just put them on the slides so that you can have a look at these. But I'm not going to go through all of them just in the interest of time. One that I am definitely going to point out is this one over here. So this is called the Pythagorean identity. Really important to know, to remember that sine squared x plus cos squared x is equal to 1, because you're potentially likely to get a question on exam 1, which might give you sine x or cos x, and they will ask you to determine what sine x is. Really common question that you're likely to get, so really important to get familiar with this particular identity. Okay, let's look at the unit circle quickly. So just basic properties of the unit circle. It's just a circle with a radius of 1. Essentially, this is 0, 1. Oh, sorry. So coordinates 1, 0, 0, 1, negative 1, 0, 0, negative 1. So you basically get the point. We have an x-axis, y-axis, just a graph, but it actually represents a circle with a radius of 1. And the main aim of the unit circle is essentially trying to find what these values are. So let's just say we know the angle that the graph makes with the origin. So the origin is at 0, 0 over here. If we know what angle a particular point on the unit circle makes with that origin, we can work out what these values are just by using the properties of sine and cos. So if we look at this, we have a triangle, which has a hypotenuse length of 1. We have this x length over here, and this y length over here. So x, y. We don't know what they are, but what we do know is the angle over here, and that it lies on the unit circle. So essentially, if we have a triangle, sorry, draw that again. Oh my god. Alright, I just accidentally deleted everything. Doesn't matter. Oh, sorry. Let me come back. Okay, so if we have, so we're trying to determine this value over here. We know what that angle is. We have formed a triangle here. So this is the x value of that coordinate, and this is the y value of that coordinate. So again, we have a triangle. And we have an x value here and a y value here. So essentially we know what this angle is, and we're trying to work out what the x and y value is, and we also know that this hypotenuse length is 1. Well, we can actually use the sine and cosine rules. Well, sine theta we know is equal to opposite over hypotenuse. So what is opposite? Opposite is y, or the length of y, over the hypotenuse 1, which is essentially just equal to y. So therefore, the y value of this coordinate is equal to sine of theta. So sine or whatever that angle is. And then if we look at cos of theta for this triangle, it's going to be adjacent over hypotenuse, which is x over 1, which is going to be equal to x. So therefore, the x value is cos theta. So therefore, these coordinates are cos theta sine theta. Essentially. But that only works in the first quadrant. Because as we go further along, the value is actually going to start and change a little bit. And that is referred to the symmetry properties. So those all the symmetry properties we sort of like, I went over there in this table over here, which you can use when you're answering questions. But right by this stage, you should all be familiar with the different symmetry properties. So depending on which quadrant we're trying to solve in, you should know if what's going to be positive. So in the first quadrant, we know that everything is positive. So all values, so sine, cosine, tangent, any values that you're trying to calculate, all of them are going to be positive. Whereas in the second quadrant, only sine is going to be positive, or in the third, only tan, and in the fourth, only cos. So let's just say we have an example. So given that cos of A is equal to 1 over 4, find sine A and sine A plus 2 pi over 2 for A is negative pi to 0. So if cos of A is equal to 0 or 1 over 4, we can use the Pythagorean identity that we looked at. So sine squared A plus cos squared A is equal to 1, which I've used over here. And that gives me a sine value of negative root 15 over 4. And now if we look at the symmetry properties, so if sine A plus pi over 2, so sine x plus pi over 2 is equal to cos over x. So therefore this should be equal to cos over A, which is equal to 1 over 4. So again, just another symmetry property thing. So when we're solving circular functions, it's really important to follow a procedure. Otherwise you're going to get, or otherwise the question is going to be getting really messy really quickly. Really important to follow a certain procedure. So the first part of the procedure is rearranging a simple equation. So if you have an equation like this, first step is always to rearrange it to just make sure that you have sine on one side and so just sine on one side and just a number on one side, usually. Next step is to find the basic angle. So what is the basic angle? So the basic angle is going to be, okay, let's just say if we have sine of x equals half. So technically, because this value can take, values in the first, second, third, or fourth quadrant, the base value is in the first rotation. What is this value going to take? Or the value in the first quadrant, essentially. And that's the one that you determine from your exact value table. So sine x equals to half. You would go to your exact value table, or if you've memorized this, sine of x is equal to half. That is pi over 6. So that's essentially what the principal or the basic angle is. And then what you need to do is you need to determine the size of the sine of the angle. So what is the sine of the angle here? So if it's so in this case, let's say it's positive x. Then it's all then you're just finding the values in where sine is positive, and we've determined that that is going to be in the second, and the first quadrant. So we're finding all the values for sine of x in the first and second quadrant for which it is equal to half. So the base angle here is going to be pi on 6. And then once we've done that, then we need to solve for x. So essentially what we do is we find the next solution. So what is the next solution here? So the first solution in the first quadrant is going to be pi on 6. What is the solution in the second quadrant going to be? Well, it's going to be pi minus pi on 6, just using the symmetry properties again. So from now, what you can actually do is once you've determined two solutions, you can literally just add 2 pi to get to the next solution. So add 2 pi to pi on 6, and then add 2 pi to get to the next solution. And then you again add 2 pi to that, and then add 2 pi to the other one, until you find all the values in the given domain. So that's how you would do it. So you would do it for as many periods as required by the domain. But you do need to find the first two values. That's the important part. Okay, so here's just a quick example of how to use the sine function, or how to solve a sine function. First step is to find what sine of 2 theta. So we're finding sine 2 theta is equal to -12. So first step is looking at whether theta is positive or, not theta's. First step would be to determine the base angle. So our value is equal to -12. So therefore our base angle is going to be pi on 6, just using our exact value table. Next, what we need to do is solve just for 2 theta. So just ignore the 2 or whatever's in the bracket for now, and we just solve for 2 theta. So we know that the value is going to lie either in the third quadrant or in the fourth quadrant. So then we just start solving for 2 theta. So we just find the first two values in the given, in the first rotation of the unit circle. So that's going to be pi plus pi on 6 and 2 pi minus pi on 6. So once we've done the first two values, we can find all the values in the given domain. And how you determine the domain if it's been adjusted is you literally just apply the same transformation. So the theta has been doubled by 2, so therefore the domain values is going to be also doubled by 2. So essentially it's 0 to 2 pi as the new domain, or the adjusted domain. So therefore we're solving 2 theta for 2 rotations, because 4 pi is 2 rotations. So therefore we will find the next two values. So that would be 7 pi on 6 plus 2 pi and 11 pi on 6 plus 2 pi. Once we've determined those, then we need to solve for theta. So all we do is we divide by 2 from all the values. And then we get 7 pi on 12, 11 pi on 12. Here it should be 11 pi on 12 plus 2 pi. That should be 7 pi on 6 plus 2 pi. My bad. Oops. 7 pi on 6 plus 12 pi on 6. That should be 19 pi on 6. And 11 pi on 6 plus 2 pi on 6 should be 23 pi on 6. So those are my values in the second rotation. And I've found all the values in the adjusted domain. Then what I need to do is I need to divide by 2 from each of them. So then it would be 19 pi on 12 and 23 pi on 12. So those are therefore my solutions. So again, let me know if you have any questions in the chat. Okay, so okay, here is a more complicated secular function solving question. So sometimes we do like to put these types of questions on the exam just to trick students. So the main important about this question is sort of to treat it as like a quadratic function almost. So first of all, we will factorize the sine of x, and that will give us sine squared x plus cos squared x. And what do we know about sine squared x plus cos squared x? Well, that's the Pythagorean identity, and that's equal to 1. So therefore, this will just get cancelled out and equal to 1. So therefore, we're just solving for sine of x is equal to 0. And then just look in your domain, where is sine x equal to 0? Well, that would be, pi, 2 pi, 3 pi, 4 pi, 5 pi, so on and so forth. And then we just write the values in the given domain, which is 2 pi, 3 pi, and 4 pi. So here it's pretty straightforward. If it was something else, you would have to treat this as sort of like a null factor law. So sine of x equals to 0, and whatever's inside this bracket equals to 0, and then go from there. Okay. So, here is how we can find the general solution. So, when we're finding the general solution, I usually don't use this formula. I've just put it there because some people like to use this formula. But, when I'm trying to find the general solution of something, what I usually do is find the first two values of that circular function, like we've done before as well. Find the first two values. So let's just say we have sine of x equals to root 3 on 2, and we've not been given a domain. So this is general solution when you've not been given a domain, but you still have to solve. First step, finding the principal or the basic angle, which is going to be pi on 3. Just looking at your exact value table. And then once you've done that, you can just solve for the first two values. So when does sine of x is equal to root 3 on 2? Or positive root 3, and that's in the first and the second quadrant. So what are the values going to be in the first and second quadrant? Well, they are going to be pi on 3 and also 2 pi on 3. So we know that once we found the values in the first quadrant and once we find the first two values, the circular function is actually just going to repeat themselves. Because once we go a full rotation around the unit circle, we get to the same value. So essentially what we can just do is we can just add by 2 pi n. And then we can add this by 2 pi n. So what this does is it gives us a general solution. So once we sub in an integer value for n, we can get the relative answers for the solution. So we can get all the values from negative infinity to positive infinity just by substituting integer values for n. And remember to write this as well. N is an integer. Okay, so here is sort of like a general question, which we won't go through, but because I've just gone through an example, but you're finding a general solution, so you would follow the exact same process. You would find the first two values, rearrange to make x the subject, and then just add 2 pi n to each of them. Essentially just it. Sometimes you will get the form a little bit different, and that's only because Vika try to trick you, essentially. That's why they often do that. Okay, so now we will look at sketching. So how do we sketch circular functions? So circular functions are probably one of the hardest to sketch on the exam, especially exam 1. But examiners are looking for scale, curvature, and asymptotic behavior when applicable. So they're really checking how your curves look. If they're, going like this, as opposed to like this. This is a big no-no. Make sure your curves are curved. And this doesn't just apply to circular functions. It can also apply to any other, mainstream function. So when you are asked to sketch, important steps. First step is to always calculate the asymptote. This is for tan, First step is to always calculate the amplitude and the period. They will really help you define what the shape is going to be. Next step will be to actually look for to determine any x-intercepts, because you will be asked to label them, any y-intercept. If the graph is translated horizontally or vertically, that might be a little bit more confusing, but just really trying to determine any x-intercepts will be really important. Any endpoints if the graph has a particular domain. So all these things are just overall going to help you sketch the graph. So we're not going to go through sketching sine and cos really in depth, just due to time restrictions, but we will have a look at the tan function quickly. So sketching tan is actually a little bit different. So if we have a function like this, so f of x is equal to a tan n x plus c, which is a general form, the first asymptote, so tan function is actually going to have asymptote because they're actually undefined at certain locations. Undefined means they can't reach that value. They will get really close to it, but they will never actually reach to it. So this is what a basic tan function looks like. Let me just draw the asymptote again. Just choose a different color. Yep, so it will look like this. Something along those lines. This is probably a bit too broad, but yeah. Has a point of inflection at this point over here. Okay, so the first asymptote in the graph will be at this point. And then you can find the next asymptote literally by just adding periods. So tan normally has a period of pi. And it's different to sine and cos, but tan actually has a period of pi. It repeats itself every pi units. So to find the next asymptote, so once you find the first asymptote, which is just going to be whatever value is inside the brackets, letting that equal to pi on 2. And we're letting that equal to pi on 2 because if this graph was actually not translated or reflected or dilated, pi on 2 would be the first asymptote for the tan x graph, just tan x by itself. So by letting this equal to nx equal plus c, we're actually accounting for those transformations and then finding the new asymptote. So once you find the first asymptote, the next asymptote is literally going to be a period away. So you just add the periods. And the period of a tan function is actually pi over n as opposed to 2 pi over n. The first x-intercept is going to be at nx plus c, so whatever's inside the bracket, letting that equal to 0. Again, because if there was no transformations, the function, the tan function would have its first x-intercept at 0. And the range for the tan function is actually r, as you can see here. It goes up to infinity and down to negative infinity. Something else to really make sure of is that your function is always approaching the asymptotes and never actually touching them. And also, you need to label your x-intercepts, your asymptotes, equations, all that sort of thing, all that sort of stuff. So here's just a practice question quickly. So if we have y equals tan x minus pi, for x is equal to 0 to 2 pi, first step, determining the asymptote. So we let the number inside the bracket equal to pi on 2. So we would get 3 pi on 2 as the first asymptote. Then to determine the period, well, the period is going to be pi on whatever number is in front of the x, which is 1. So it's just going to be pi in this case. So to work out the next asymptote, we'll literally just add pi. So it will be 5 pi on 2. And also you can go backwards as well. So subtracting pi. So pi on 2. So on and so forth. But we're only drawing from 0 to 2 pi. So just really in count for that. But if you really think about this graph, it's just tan x minus pi. And what's the period of pi? It's pi, right? So essentially we're just translating the graph pi units across to the right. So we're not really affecting the graph at all because the period is pi. So we're essentially just shifting it one period down. So the graph will look exactly the same. And as you can see here, it just looks like the normal tan x function. Okay, so here are the key takeaways for this block. So really being familiar with sketching graphs, so their shape, their scale, the asymptotic behaviors, how to label equations of asymptotes and coordinates when you're sketching. Really important for exam 1, but as well as exam 2 as well. Solving, really important to be looking at the underlying domains. Some values will not, or some functions will not give you explicit domains, So in that case, you will need to rely on underlying domains. You will have to identify underlying domains. Also, when you're solving inequalities, do not put equal signs between quantities that are not equal. A lot of students end up doing that when they're solving a really big equation. They end up putting equal signs for things that are not equal to each other. So that's just more of a notation thing, I would say. And transformations. So really being aware of the transformations and what the transformations are, how you can go from a worded question, which gives you transformations, to then applying those transformations to a graph, either using the coordinate method, which I would recommend, or using the function notation method. So those are the key takeaways for that part of the functions and algebra part of this lecture. Now we'll be moving on to calculus. So the thing about methods is everything is integrated. So you're not going to get a question just about functions. It's going to be combining all the skills that you've learned throughout the year. And calculus is, I would say, something that's going to bleach into everything that you do. So it's going to be in literally every single question that you answer, or in most of them, especially in exam 2, I would say. So now we're going to be looking at the differentiation, and applications of differentiation. We're going to understand the implications of the derivative. So what does the derivative actually mean? Derivation of basic derivatives, and also the different types of notations of derivatives. Then we'll be looking at the chain, product, and quotient rules, tangents and normals, and rates of change, as well as stationary points. And then we'll look at integration and application, so understanding the implications of an integral, understanding basic antiderivatives and the fundamental theorem of calculus, as well as area bounded by curves and the average value. So differentiation is essentially allowing us to work out the tangent of a function, or the change that a function goes, which is essentially what the tangent is. And the rate of change that we're actually looking at is the instantaneous rate of change. So let me try and actually illustrate what that actually means. So if we have a linear function, it actually has a uniform gradient, right? So the gradient at this point is going to be the same as the gradient at this point. The gradient is not changing. But, however, if you have something like this, the gradient at this point is certainly not the same as the gradient at this point. You can clearly see that this is going to be a positive gradient, and this is going to be a negative gradient. So what what derivatives or calculus allows us to do is allows us to work out what the gradient is at this point, and that uses something called first principles. So what first principles, which you don't need to know for year 12, essentially is basically we're trying to work out, so let's just say instead of working out the gradient at this point, we might want to work out an average between these 2 points. But we want to get even closer, so we might do between these 2 points. So now we're getting closer to the estimation of the gradient. Then we might do a point over here. Now we're getting even more closer. And then we might do a value closer and closer and closer. But essentially, we want to be as close as possible, which we cannot achieve. So what we do is we do limit equals 0. So basically the difference between that value and another value is just 0. So essentially we're finding what's the gradient at that particular point. So this is essentially, you don't need to know this in a lot of detail, but this is essentially how we derive, how we get derivatives. So this is the first principles. Okay, so here are the different types of notation. So if we have so this is what function notation will look like. So we have, let me use a different color. So for function notation, we will usually have stuff like f of x is equal to this. What is the derivative? Why does it keep on going back? F of x is equal to this. What is f dash of x? F of dash of x is how we denote the derivative of a function that's given in the form of f of x. Next, if we look at how to actually denote, so let's just say we're trying to work out the gradient at a particular point, we can substitute that value like this. So we can just write f dash slash a, and that's literally it. For y, so if we have something like y equals something, how we denote the derivative is dy on dx. So that's how we denote the derivative. And then finally, how do we denote a value that we're trying to sub in to find the gradient wall? Well, what we can do is dy on dx. Well, usually a lot of people don't do this, but but you can do this. You can do dy on dx given x is equal to a. So now you're showing that you're substituting a into whatever the derivative is. So that's just some notation. And now we'll look at the different derivatives. So all of these derivatives are actually given to you in your formula sheet, which is great for both exam 1 and exam 2. You don't have to memorize anything. But basically, so I'm not going to go through all of them. I'm just going to go through some of the important ones. So for x of n, just a basic function, the derivative is going to be equal to n. So what we do is we drop the power and then we subtract 1 from the power. That's essentially how we get a derivative. And then if we have something like this, so we'll come back to that in a second. Yeah, so these are just so these are actually not the rules that you actually get given in your formula sheet. These actually combine the product and quotient rule, or the, so these actually combine something called the chain rule, which we'll have a look at in a second. But if you're finding e to the power of gx, what you need to do is you need to put the derivative down in front of the ex, and then you need to leave the g of x. Similarly, if you have sine a of x, you need to drive whatever's inside the function, put that in front of the function. And then if you have sine x, ooh, that's a bit strange. Sine x, actually when you derive it, becomes cos x. And cos x, when you derive it, actually becomes sine x. So I don't know why that's the case, why it's been misinterpreted. But yeah, so you have all these formulas in your formula sheet. That was my main point here. Okay, so let's look at a chain rule question. So in the first question of the exam, you'll get a question like this. Some form of derivative calculation. So let's have a go at this question here quickly. So if you're, first step, we have function. So really important to notice here, we actually have y equals e of x. So when you're denoting the derivative, you write it in the form of dy equals dy dx. So essentially what we do is dy dx is equal to d of dx. So here we're actually using the chain rule. So what the chain rule essentially is when we have a function inside of another function. So if we have, for example, in this case, e to the gx. So the function is, e to the power of x, and then we have g of x inside of e of x. So what we can actually do is use something called the chain rule. So the chain rule essentially is if we have dy, if we want to work out dy over dx, that is equal to d of dy on du, which is also given in your formula sheet, and which we're going to go through in the next slide, times du on dx. So what is going to be u here? So you need to let something equal to u, which is obviously going to be this function here. Because from the normal derivative sort of formulas that you're given in your formula sheet, you can't actually solve something like this. So essentially what you're going to do is you're going to look in your, you're going to let g of x is equal to u. So let u equals g of x. And then we get y equals to e to the power of u instead of e to the power of g of x. So then the next step will just be to derive using the chain rule. So dy on du. So what's dy on du? Pretty straightforward. It's just going to be e on u. So dy on du is just equal to e on u. Multiplied by du on dx. What is du on dx equal to? Well, it's just going to be the derivative of this function over here, g of x. So you multiply by that. And that is essentially what's been done here. So we have d dx of whatever was u multiplied by e of u. And then we get this. Okay, so now let's look at the different rules in a little bit more detail. So these are all given in your formula sheet. So you can apply them. So you can either use the function notation or the Leibniz notation. I personally like to use the Leibniz notation just because I find it a little bit more easier to realize what's happening. This just looks really super messy to me. But depending on what type of question you have, you can use either one. Okay, so now we're going to be actually looking at what calculus or derivatives can allow us to find. And that is the tangents to a particular point, which is what we were trying to find. What is the gradient at this point here? So derivatives will give you the gradient at that point, but from the derivative or the gradient at that point, we can determine the tangent. So if you're not sure what a tangent is, it's basically a linear line, which shares a common point and gradient at that said point. So for example, on this polynomial, if we're trying to determine the tangent to this point over here, it will share, first of all, this coordinate. So the coordinates will be the same. And also the gradient at this point will be the same. So we can determine from this polynomial, we can derive it and we can determine what the derivative is equal to at this point. We can then sub it into y equals f of x in order to determine, we can find the gradient at this point, and then we can use just normal linear equation to determine what the actual tangent line is equal to. And that will look something along the lines of this. So the y tangent, the tangent at this point will be equal to f dash of a, so the gradient multiplied by x minus a plus f of a. So here is a formula that you can use to determine gradients. Alternatively, once you find the gradient, it's just going to be y minus y1 equals to m x minus x1, essentially, where x1 and y1 are the actual coordinates at this point, and m is just the gradient at that point. Okay, so now we'll look at normal. So normal is essentially where we share the same point, but it's actually now perpendicular to the tangent. So like a tangent, but now it's perpendicular at that said point. So then the gradient now is actually going to be the perpendicular gradient. And the way that we determine the perpendicular gradient is essentially by using this formula. So the function, the gradient of the tangent multiplied by the gradient of the normal is equal to the -1. So essentially the gradient of the normal is just going to be the negative reciprocal of the gradient of the tangent, effectively. And then the remaining process is exactly the same. So once you've determined the gradient of the normal, you can sub back in the points, or you can either use y minus y1 is equal to m of the perpendicular gradient x minus x1. Again, just differences in notation here, but same sort of process. So here is a quick question. So find the tangent and normal to f of x. And f of x is x minus 2, x minus 3, at x equals to 1. First step would be to derive this function. So when we derive this function, we are going to get, so when we derive this function, we will get f dash x, and then we're determining, since the gradient at f of 1, we can just sub that in. So whatever we get for f dash of 1, let's just say that is equal to a, that is going to be the gradient of the tangent. So then the point, so what is the point at f of 1? We need the coordinates. So we have the x coordinate, but we can determine the y coordinate by subbing it in. So essentially the tangent line is just going to be y is equal to f dash of 1, 1 minus x, sorry, the other way around, x minus x1 x minus x of 1 plus f of 1. So that is just what the equation of the tangent will be. Y is equal to the gradient of that point, x minus 1 plus f of 1. So if you're not familiar with this, just look at the previous slide. This is how we derived it. And the normal will essentially just be the perpendicular gradient. So remember, the perpendicular gradient is just the negative reciprocal of the tangent gradient. So therefore, the line is going to be negative 1 over f dash of 1. So obviously I haven't found the values here, but you can go ahead and find these values and, you know, find out what they're actually going to be. But I'm just not going to find the values in the interest of time. So therefore, it should be plus f of 1. So this is what the normal line is going to be, the equation, and this is what the tangent line equation is going to be, which come out to x plus 1 and 3 minus x. Okay, so now we'll look at rates of change. So we've sort of looked at rates of change already. So it's just looking at how do values change over time, essentially, or in a graph. How do the y values change as the x values are changing? And there can be two types of rates of change. So first is the instantaneous rate of change, which is what we were looking at, which is the derivative at that point. Or there can be the average rate of change. So let's just say I have a graph and I want to determine the average rate of change between -2 and, you know, +4, for example. So let's say this coordinate is -2, -6, and this coordinate is 4, 4. So if we're determining the rates of change, we can use this formula over here, where we do the highest value first, the f of b. So what's the y value? Essentially what we're doing here, if you didn't notice already, is we're working out the gradient between those 2 points. So from just basic linear equations, if you have 2 points, you can easily determine the gradient. Just doing rise over run, or y minus y1, or y2 minus y1 is equal to x2 minus x1. So if you let this is equal to x1 and x2, and this equal to, x1 and y1, and this equal to y1 and y2, you can easily just solve this function. So pretty straightforward for average rate of change, and instantaneous rate of change is just the derivative at that point. Okay, now let's look at stationary points. So stationary points are essentially where the graph has a gradient of 0, essentially. So we can either have local minima, we can have local maxima, or we can have stationary points of inflection. So as the name suggests, the local minima is essentially where you have a negative gradient, it reaches a gradient of 0, and then it starts becoming positive and more positive. Local maxima is where we reach a maximum point, which is not the end point. Really important. Local maxima and local minima are not the end points, because the graph is continuing. But it's just the nature of how the graph. So we have an increasing gradient, so the gradient is getting more and more positive, or sorry, less and less positive, I should say. But sort of positive, then it reaches 0 point, and then it starts going negative again. Similarly for stationary points of inflection, they are actually increase, stop, increase, or decrease, 0, decrease. So a little bit different to local maxima and minima. But we'll have a look at how we can determine which one we have. Okay, so we can use the nature table, which we won't have time to go through today. But the nature table is essentially when, let's just say we have a stationary point at f of dash is equal to 0. So f dash of 0 is equal to 0, okay? So you can draw up a nature table quickly. So we have f dashes, so we have 0, and let's say at that point we have a stationary point. So we can do something that is less than 0 and something that is greater than 0. Something very sort of close, right? Like -1 and +1. And then we can determine if the gradient at those points is negative, positive, or, you know, well, they won't be 0, but are they negative or positive? So if you get something like, negative and then positive, then you can sort of see that it sort of forms like a local minima. So therefore, the nature of that gradient is going to be a local minima. So I personally always use nature tables. You can also use second derivatives, but I personally won't be going through since it's not part of the Year 12 study design. But if you do know how to use it, go ahead. So that's also a good method. Okay, so now we'll look at absolute maxima and minima. So absolute maxima and minima is essentially just the absolute maximum or the most maximum or the most minimum value in the entire graph. So if I was to use a quick example, just say my values. So let's just say this is my graph. I have two endpoints here. But when I'm trying to determine the absolute maximum, I'm looking at what point is the highest out of all of them and what point is the lowest. So this point over here is the lowest. So this would be the absolute minima. And this value actually here is higher than the endpoint. So therefore that would actually be the absolute maximum. And that is also a local maximum as well. So a local maximum can also be a absolute maximum as well, just depends on the graph. Okay, so here are just some sort of like basic rules. So if the absolute maximum value occurs at x equals a, f of a is going to be greater than f of b for all acceptable values of b. So essentially what this is saying is, let's just say we have the absolute maximum at this point over here. All the y values are going to be greater than any other point on the x-axis or on the y-axis. So if this is b or this is b, f of a will always be greater. Similarly, for a local minima, the y value at this point will always be lower than the y values at all of these other values. Essentially what the definition means. And the absolute maximum / minimum will always occur at a stationary point or an endpoint. Either of those two, but a mixture also as well. It could be at a mixture of those two, but none of the other points are going to give us a absolute or a maximum or a minimum. Okay, so here's just a quick example. What would be the absolute maximum and minima? Well, whenever we're just trying to determine the absolute maximum and minima, we always need to work out the endpoints first of all, and then we also need to determine any stationary points. And then we compare the y value. So the lowest y value will be over here. So therefore we have our local, our absolute minima being our local minima, which was 0,1, I believe. And then the absolute maxima is going to be at the right endpoint over here. That's the highest value that we have, or the highest y value. So therefore the absolute maxima is going to be the 10. And this is really helpful because this also helps us to determine the range of a function. The range of a function is essentially just the absolute minima and the absolute maxima. Okay, so that was essentially it for differentiation. Now we'll look at anti-differentiation. So the anti-differentiation, like the name suggests, is the opposite of differentiation. And what it's useful for is determining the area underneath a graph. So the dx at the end indicates the variable in question. So if we're trying to determine the antiderivative of f of x, we need to have fx at the end because that's the variable that we're trying to determine the antiderivative for. So again, sort of like coming back to notation, if we have an integral sign, it will always be followed by a d something. You can't just have an integral sign and not follow it by anything. And also when you're anti-deriving, remember what we do is if we have a to the power of, we'll come back to the rules later, but if you have a to the power of n, what we do is we add 1 to the power, opposite of derivatives, we divide by the power. But remember, essentially when we derive, if there are any constants, we're actually just losing them. So therefore we need to account for that by adding c at the end of the antiderivative. And by doing this, what we are doing is accounting for any constants that we may have basically lost when we were deriving, essentially. Because when we antiderive, the c could be literally so many numbers. It could be plus 2, plus 3, plus 5, plus 100, plus 500. So we need to account for that by adding the plus c. Okay, so what is the derivative of 2x? So the derivative of 2x is equal to 2, right? But what is the derivative of 2x plus 1? It is also equal to 2. So therefore, these two are both the same, although we have different constants. For this one, it's plus 0, this one, it's plus 1. So this is essentially the reason why we need to add plus c at the end every time we antiderive. Here are all the formulas that are also found in your formula sheet. I just put them there just in case, but we won't be going through them. So all of these formulas are in your formula sheet, so use them when you need to use them. Okay, so let's just go through the fundamental theorem of calculus. So the fundamental theorem of calculus is essentially where we have definite integrals. So indefinite integrals is essentially what we were looking at before, where we don't have any values that we're sort of anti-deriving for. We're just solving for a general antiderivative. When we have these limits, so these are actually called limits, we are now finding a definite integral. So we will actually get a numerical answer at the end. And that is essentially just the area underneath the graph, essentially. But the way that sort of works is when we have a to the power of lower limit a, upper limit b, f of x equals dx, first step is anti-deriving. So we just anti-derive f of x using these formulas over here. And then we put the limits here. And then what we do is we actually substitute these limits into the antiderivative. So then we do f of b, so capital FB minus capital FA, where the capital F represents it's a antiderivative as opposed to just a normal function. So this rule is super duper important. It has been coming in methods exams every single year, and it's the fundamental theorem of calculus. So really get familiar with this, which I'm pretty sure you all will be. So here's just an example of a scenario where we might need to use it. So let's just say we have 0 to the power of 5 f of x dx is equal to 5, and we want to find what 0 to 1 f of 5x dx will be equal to. Sorry, I think there's something wrong. Oh no, that's correct. So 0 to the power of 5 f of x dx is equal to uppercase f, so the antiderivative of f of x. So we sub in f and we sub in 0 and we get equal to 5, as it's shown in this question over here. So if we're solving for 0 to the power of 1 f of x, what we are essentially doing is we're solving for 1 over 5. So we're looking at the transformations that have been applied to the graph, and we're essentially reversing the transformations. And then we're doing f of 5 minus f of 0, and we should get 1 as our answer. So that question is definitely a little bit more complicated. What we usually do is, or what I usually do is, we need to know that these limits are actually for x. So this is actually x is equal to 0, and this is x is equal to 5. Right? So if we have f of 5 of x, essentially 0 to 1 f of 5 of x, what we can actually do is sorry, what was the function again? F of 5 of x dx. So what we can actually do is we can let u equal to 5 of x. So now the limits will also be in terms of u. So u is equal to 5 of x. So what is that? What is u when x is equal to 0? So it's just going to be 0. And then since we were solving for 1, 0 to 1, 1 times 5 would be 5 f of x. F of u now. D. And we're also now solving for du. So we can solve this. It's just going to be equal to 5. But we need to remember that we need to divide by 5. So this is more so special, I would say. So if you don't understand this, you're not really going to get a question like this on the exam. It's just to sort of understand how the fundamental theorem of calculus sort of works. But then we need to divide by 5, and that is how we will get 1, essentially. But if you do special, you'll know what I'm talking about. Okay, so for any function, the integral is essentially just the signed area. So if we have something like this, and we're trying to determine the area between this point and this point, we're actually going to determine this area over here. This area and, this area. So this area, we're actually going to get negative. So essentially it's just going to be this area minus this area, which is not what we want. So we want the signed area. Yeah, so we want the unsigned area. So the signed area is essentially when we're literally just doing a to b, f of x, and we're getting the area. So between a and b, so what's the area of f of x, the function f of x, between a and b? We find the antiderivative, we sub in b and a. Pretty straightforward. But if we want to, if a is, for example, down there, and b is over here, and we want to determine what this entire area will be, as opposed to just this minus this, we can actually sign it, because we know that these values from this point to this point is actually going to be negative. So these values are actually going to be negative, and these values are actually going to be positive. So essentially what we can do instead is, so here's just some properties of the function, because essentially what we can do is, we come back to here, we can divide it up. So let's just say it was a to b. So we can actually divide this up. So we know that this value over here is like 2, let's just say, or negative 2. So we can find the area from negative a to negative 2 and make that actually negative. Put a negative sign in the front, because negative and the area which you're going to get is negative will make a positive. This is actually going to give you a signed area, which is going to be positive, or unsigned area. So negative a to 2 of f of x, and then you can just add the rest of the area, which is going to be negative 2 to b f of x d of x, so on and so forth. So this way what we're doing is, instead of finding the negative area, we're essentially just finding the positive area. So we'll come back to another example in a second, but here's just some of the properties of the definite integral. So the definite integral from one number to itself is just going to be 0. Makes sense. We're not covering any area. The antiderivative from a to f of x. So if we have a constant in front of the f of x, we can actually move that out, solve for the antiderivative, and just multiply it in. Same thing. And if we have two lower limit and upper limit, and if we swap them, we are going to get the negative of the end of the integral of this. So that was essentially definite integrals. We are now going to look at what I mean by splitting up the areas. So when we have a function like this and we're trying to determine the area, the shaded area essentially, between two different curves. So when we're trying to determine the area between two different curves, sorry, this is a little bit distorted, but let's just say we're trying to determine this area here. So it's not between that area, that function, and the axes. It's instead between this top function over here, which is f of x, and this line over here, which is g of x. So essentially what we can do is we can determine, let me just rub this out quickly. We can determine what this orange area would be all the way to this value, so this entire region. So essentially what we will just do is derive f of x from 0 to 0.75, essentially. And that will give us this entire area. Then what we can do is we can subtract that bottom area, that triangle, because that will essentially just be the area under underneath this linear line. So once we do that, we will get the overall area between the two curves. So it will literally just be f of x minus g of x between the two intersection points, which will give us 2.87. So it's just the upper function, subtract the lower function, and your answer will always be positive in this case, if you're doing upper minus lower function, regardless of whether it's below the axes or above the axes. And thus this shaded region over here, the way that you can actually find this area is actually doing negative integral 1 to 3. And it's negative because if you just did 1 to 3 f of x, you will actually get a negative area. So in order to make that positive, we add a negative at the front, just to find this particular shaded area over here, not the one that we calculated before. So this is essentially what this area is going to be over here. So I hope that makes sense. Okay, another thing that you will need to calculate is the average value, and there's a formula in your formula sheet for this. So the average value is literally just, if we have a graph like this, what is the average value in this region? Or sort of like, you can think of it as sort of like the mean, almost, of this graph. And the formula as it goes is 1 over b minus a, integral a to b. So whatever region you're trying to determine the average for, b is the highest value and a is the lowest value. And then the lower limit to the upper limit, f of x. Pretty straightforward, just subbing in the formula and you should get the exact value. So it is easier to remember where the average value formula comes from rather than what it is, because it is important, it's not the average value or it's not the average rate of change. Really important. The average rate of change is how the gradient changes, or what's the average gradient. Average value is the actual average of the values in a particular graph. Okay, so here is just a diagram that I drew for the average value. So essentially, if we're trying to determine the average value between a and b, it's just going to be integral a to b, 1b minus a. So now we're going to just look at the quick, move on to the probability section, but just the key takeaways from the calculus section is notation must be consistent throughout the entire question, and really being spot on with the notation will really help you not only know what you're actually doing, but also for your examiner who's marking it as well. And in terms of integrals, remember if you have an integrand, follow that by a dx sign. Don't just have one or the other. And also remember the plus c when you're doing an indefinite integral. And also just in terms of areas as well, I would recommend actually drawing out the function that you're determining the areas for so that you can determine what actual area you're determining, as opposed to just two random functions which you're trying to determine the area for. Okay, let's quickly look at probability. So probability in essence is just the chance of success for a particular event. So the way that we determine probability is just the number of successful states or the number of successful outcomes in over the total outcomes. Pretty straightforward. You should all be familiar with what probability is. Here are just some fundamental properties of probability. So obviously the probability of a particular event is going to be between 0 and 1, and the total probability is going to equal to 1. Here we just have the conditional probability formula, which we'll come back to in a second. And lastly, here is the addition formula rule, which is in your formula sheet, or you should have this somewhere in your formula sheet. This is really important when we just get simple probability scenarios and we have to determine A or B or A and B or something along those lines. And this only works for independent scenarios or independent outcomes. Independent outcomes. Okay, so just looking at the intersection quickly. So intersection is basically just the number of, so let's just say we have events A being even numbers on a dice, event B being the first three numbers. The intersection is essentially what outcomes or what variables or what elements actually satisfy both of those scenarios, essentially. And really important when we're working out the probability A and B, we're just looking at the intersection, or what is the probability or the chance that both of the elements are chosen together. This is different to probability A or B, which is essentially what's the probability that we get A or B, essentially, or this actually determine the union. But essentially, let's just say we have, I always like to depict it using a Venn diagram. Let's say we have A and B. So probability in A intersection B is this region in the middle. So what is the probability that, it's going to be A and B at the same time? Whereas A or B, it could either be A, just A by itself, or it could be B just by itself, or it could be A and B. So it's in this entire region, the two circles combined. So that's essentially probability A or B, and we can determine that using this formula over here. Okay, so next we'll just quickly look at conditional probability. So conditional probability is essentially just when you have a certain criteria and you're trying to determine, so you have this overall criteria and you have a specific criteria within that, and you're trying to determine what is the probability that my element or my value is going to be within that, what's the probability that my value is going to be within that criteria, within that particular criteria, within this overall criteria. So what is the probability that my a particular value or a particular event is going to occur, assuming that the condition or a certain event has already occurred? So a probability, an example with that would be, let's assume it's raining already. What is the probability of me taking an umbrella, for example, if it's raining already? That would be something like conditional probability. The condition is what's the probability of me taking an umbrella given that it's raining, as opposed to me just taking an umbrella because, I could either take the umbrella when it's sunny or when it's rainy. So we are only determining the probability of me taking an umbrella when it's raining, which would be very high, obviously. Okay, so if two events are independent, we can actually use this formula over here. Probability A given B is actually going to be probability A. And there's actually a formula that we can deduce from this formula, which is really important when we're sort of, and the question that you're going to get on the exam is prove that, events A and B are independent. And the way that we can prove this is if we just have like a Venn diagram and we know what probability A and B is, we can determine what probability A and B is from using this formula. And then if they are equal to it's the same number, then we can say that these events are independent. So essentially, if two events are independent, probability A and B is going to be equal to probability A times by probability B. Okay, so next, we can look at mutually exclusive events. So these are events that cannot occur together. So for example, it raining and it being sunny at the same time. All that technically can happen, but just for this case, let's just pretend that it can't happen at the same time. You can't be, full thunderstorm, rainy, and sunny at the same time. Those are two mutually exclusive events. So the probability of A and B is just going to be 0 because they can't occur together. And therefore, if we're trying to determine the probability of A occurring or B occurring, it's just going to be probability A plus probability B because there's no probability A and B. Okay, so now let's look at the different distributions of probability. So we can either have probability being distributed binomially or normally, which we'll have a look at a little bit later on. So binomial distribution is essentially where we have n independent trials. So independent trials means one trial does not affect the outcome of another, and each trial only has two outcomes, either success or failure most of the time. So, and the success of and the probability of success is the same each time as well. So 3 requirements must be met in order to be a binomial distribution. So first, there needs to be, the trials need to be independent. The individual trials need to be independent. So one trial does not affect the outcome of another. The probability of success needs to be the same each time. So if you're rolling a die, the probability of getting a 1 is an independent trial. So each time you roll a die, the probability of getting a 1 should be the same. And each trial should only have 2 outcomes. So for example, heads or tails. Tossing a head or a tail would be an example of a binomial distribution, where the probability of getting a head or a tail is the same every time. So, before you get started with a binomial distribution question, notation is super, super important. So whenever we get a binomial distribution question, always denote it like this. X, or the probability or the distribution of X, is binomially distributed, where n represents the number of trials that we have, and p represents the probability of success. Okay, so this is essentially the binomial distribution formula. And in this case, we need to use combination. So essentially what we're doing is, what's the probability of us choosing? So n is the total number of trials. What's the probability of us getting... So I'm just going to use a particular example. So let's just say we're tossing a die. Sorry, not a die. Let's just say we're tossing... let's just say we're tossing a die. And let's just say our particular event is getting a 1. We're either getting a 1 or we're not getting a 1. So let's just say we toss the die 10 times. And X is what we're trying to determine. What's the probability that we get... what's the probability that we get a 1 maybe like 4 times out of the 10 times? So n choose X would be n, where n represents the total number, so 10 trials, choosing only 4 trials, so getting 4 over n. And we multiply that with the probability of getting, 4, or the probability of being successful, multiplying that, so the probability of success is, 0.1 over 6. And we're putting it to the power of how many times we want to get that correct, or want to get that outcome. So 4 times. So p of x to the power, p to the power of 4, and then we multiply that by the probability of not getting 6, which would be 5 over 6 to the power of however many outcomes we don't want 6 for. We don't want 1/4, so that would be to the power of 6. But you don't need to use this formula. You can use... So most of the time you can use your calculator. There is a binomial distribution function which does this formula for you. So here is a quick sort of example. So every time Shania does her homework, there is a 25% chance that she will require some help. She does homework every weeknight for 1 hour at a time. What is the probability that she doesn't need help a single time from Monday to Sunday? So, first of all, is this a binomial distribution or not? And yes, it is, because we only have 2 outcomes. She does need help or she doesn't need help. And is the probability the same every time? Yes. So there's only a 25% chance every night that she needs help or she doesn't need help. And how many trials do we have? And are the trials independent? Yes. Well, the probability that she will require help on Monday will be the same as the probability that she will require help on Tuesday. And that will be the same as the probability that she will require help on Wednesday. And so on and so forth. So first of all, let's define it. So we have X. Let's just say X is the number of nights that she needs help for. Or she doesn't need help for. Sorry, that's the event we're looking for. She doesn't need help. So we know that it's binomially distributed. So we say it's approximately binomially distributed. And brackets, so what's the number of trials? So Monday, Tuesday, Wednesday, Thursday, Friday. That's 5 trials. And what's the probability of success? So what's the probability that she doesn't need help? So there is a 25% chance that she will require help. So you can either do it this 2 ways. So the way that I've done it is the event is she does need help. So that's why my probability of success is 1/4. And then I'm just finding probability X is equal to 0. So that's that. So essentially she doesn't need help any of the nights. So X equals 0. So essentially I'm just having it into the formula. So 5 choose 0 multiplied by the probability of success, the power of whatever I'm trying to determine, to the power of 0, because I want her to not require help 0 times and then require help 5 times, essentially. And if you're confused, the binomial distribution is actually derived from the tree diagram. So that's why we have these sort of probabilities to the power of something. Okay, here we have another example. So X is binomially distributed with 3 chances, and the probability of success is 1/4. So 3 trials in this case. So we can have conditional probability again. So what's the probability that X is equal to 3 given that X is greater than or equal to 1? So essentially, all we're trying to determine is what's the probability X is equal to 3 over the probability X is greater than or equal to 1. And essentially we can just find probability X equals to 3. And to find probability X is greater than or equal to 1, we can actually use this formula over here, which is the complement formula. So instead of finding probability X is greater than or equal to 1, sometimes it's actually easier to work out what probability 1 minus probability. So what is the opposite? What's the complement? That it's less than 1, which is essentially what's the probability X is equal to 0. Sorry, X is equal to 0, not probability of 0. So sometimes it might be easier to work out what this is. So we can easily find what probability X is equal to 0 is, and then we can subtract that. And that will give us this. So depending on the scenario, it will be really important to just know what sort of formula you're using, or what formula will be better to use. Okay, so we can either have binomial PDF or CDF depending on what you're trying to work out. So if you're trying to determine what the value is at a certain point, so what is the probability that we get X equals 1? That will actually be particular value. So that's binomial PDF, which you'll be using on your calculator. But if we're trying to determine what's the probability X is, let's just say greater than or equal to 2, that is CDF. So in this case, you will have upper and lower limits. So the lower limit will probably be 2, and the upper limit will be whatever the number of trials is. So let's say 5 in this case. And that is what you'll be inputting into the binomial CDF. So let's just say we want to find probability X, or X is equal to 2, given that X is binomially distributed with the number of trials being 4 and the probability of success being 0.703. So on the CAS, we will use binomial PDF. So the number of trials is 4, the probability of success is 0.703, and the X value in this case is actually going to be 2, because that's what we're trying to determine. X is equal to 2. So we just put this on a calculator, we should get 0.262. So you shouldn't be doing this by hand. You should, and using the formula. So you should be doing it, all the questions on your CAS most of the time. However, if we're trying to determine what X is, what probability of X is greater than 2 would be equal to, all we need to do again is use binomial CDF this time. And this time the lower bound will be 3 because determining greater than 2. Upper bound will be the number of trials, which is 4. And this time we should get 0.657. So hopefully you guys are able to understand the difference between binomial PDF, and binomial CDF. Okay, so here's just a practice question. Obviously, so if you're doing this at home, have a go at it. But obviously I have the solutions on the screen. So each year, a detailed study is conducted on a random sample of 36 Lawrence birdwing butterflies in town A. So Lawrence a Lawrence birdwing butterfly is considered to be very large if the wingspan is greater than 17.5 centimeters. The probability that the wingspan of any Lawrence birdwing butterfly in town A is greater than 7.5 centimeters is 0.0527, correct to 4 decimal places. And we are trying to determine what the probability that 3 or more butterflies in a random sample of 36 Lawrence birdwing butterfly from town A are very large, correct to 4 decimal places. So first of all, let's just define it. So X is binomially distributed. What's the number of trials? Well, we're determining it out of 36. So therefore, the number of trials is 36. What's the probability of success? Well, it's 0.0527, or just given in the question. Next, we're trying to determine the probability that it's greater than or equal to 3. So we just do greater than or equal to 3 on a calculator, and we should get 0.2947. With the lower bounds being 3 and the upper bounds being 36 for binomial CDF. Okay, question II is now a little bit of a trickier question. So the probability that n or more butterflies in a random sample of 36 Lawrence butterfly from town A are very large is less than 1%. So essentially what we have here is probability X is greater than or equal to n, which is less than 0.01. So we don't know what n is, but we do know that it's the probability is going to be less than 0.01. So what we can do is a little bit of trial and error. So just subbing in different values for n to see what gives you less than 0.01. Alternatively, what you can do is, and what I've done here is define the function, whatever you get here, so probability x of n using the formula, so the formula that we saw before, where we have the n choose x, p of x, 1 minus p to the power of n minus x. So either using that formula there, n minus x, so you know what n is, you know what x is, you don't know what n is, n in this case represents x. So you don't know what x is, but we do know what n is, we do know what p is, and we do know what we don't know what n minus x is. So what you can actually do in this case is try to use a little bit of just algebra, basically. Alternatively, what you can do is trial and error. So try and subbing in different values for n into your calculator to see what gives you less than 0.01. And in this case, that would be n equals 7. So again, let me know if you have any questions in the chat. Otherwise, we'll look at the expected value. So the mean of a binomial distribution is essentially just the number of trials multiplied by the probability of success, which sort of makes sense as well, because the number of successes that we're going to get is just going to be the number of, or the number of expected amount of successes is essentially just going to be the number of trials that we're running. So if the probability of success for one trial is 0.2, if it's 2 trials, then it's going to be 2 times 0.2, which is 0.4, so on and so forth. So binomial questions are the hardest, and the expected value, just in case, it can be greater than 1. So a lot of people get confused. So the expected value can be greater than 1. Binomial distributions, just want to give everyone a heads up, tend to be disguised in the question. So they're not going to be explicitly stated to you. So it might be related to, for example, a normal distribution question, and then it ends up being a binomial distribution question. So really trying to recognize when a question is about a binomial distribution is really important in this case. Okay, so let's just quickly go over variance. So variance is essentially just a measure of the spread of the data. And in this case, for a normal distribution, it's just going to be NP 1 minus P. So this formula is given in your formula sheet, so just using that formula to work out the variance. And then we can work out standard deviation, which is essentially just the square root of the variance, which in this case is going to be NP square root of NP 1 minus P. So I'm not going to go through that in a lot of detail, but essentially just using the formula there. Okay, so now we'll quickly skim over the normal distribution. So the normal distribution is just a type of continuous variable distribution. So a continuous variable distribution is essentially where we're recording stuff like height, weight, stuff that usually has a lot of variation in nature, essentially. And we're essentially just, so in a normal distribution, the mean is going to be equal to the median, which is going to be equal to the mode. So really important to know that in the normal distribution, the graph is actually approximately symmetrical about the mean, which we'll have a look at in the next slide. But when we're again defining the function x, we can again define it as normally. So we can say it's normally distributed. And in the brackets, we have the mean, comma, the variance, not the standard deviation. A lot of people just write standard deviation. That's the wrong notation. So this is what the normal distribution looks like. So we have 0, and then we have +1 and -1, which represents the standard deviations. So 1 standard deviation either side of the mean, 2 standard deviations either side of the mean, 3 standard deviations either side of the mean, and so on and so forth. And scientists or statisticians have actually developed a rule that can actually help you to determine what percentage of the data, or what percentage of, what percentage of the data will lie, or will have the probability of lying under a certain standard deviation. So within 1 standard deviation either side of the mean, we will have 68% of the data lying there. And the probability that values will be between -2 and +2 will be 95%. And then between 3 standard deviations, it will be 99.7%. So these are just estimates which we can use, but they're not going to be accurate. So when you are given a normal distribution, you can actually standardize it to the standard normal distribution. The standard normal distribution is essentially a graph where the mean, median, and mode are all equal to 0, and the standard deviation is equal to 1. And how can we standardize it? Well, we can use the z-score. So the z-score is essentially where we're following this formula, z equals to the x value for your function minus the mean of that function divided by the standard deviation. This way we can standardize the value, and we will get something along the lines of between -3, usually. So you will get something on the lines of between -3 and +3, and that will tell you, where your data is sort of sitting. So if you get like -1.2, that will tell you that your data is 1.2 standard deviations of the mean of your data. And if you get a value of, let's say 2, for example, that would mean that your data is 2 standard deviations above the mean. And then from this, we can compare the normal standard deviation. We can compare the standard normal distribution from the normal distribution that you're given. Okay, so that was essentially the probability section. I just like to give everyone a few exam tips before your exam. So use reading time effectively. So reading time is so important for the methods exam, because you would have to read through so many questions, try to understand, what sort of questions you might struggle with, what are the easy questions that you can get straight away. Read the long-worded questions, especially the probability ones, because they will have a lot of words, and you're trying to really determine what are the mathematical skills that they're trying to essentially get from you. Okay. Next, when you're doing the actual exam, begin with questions you immediately know how to do. So those might be, for example, for me, those are the probability questions. I found them always really easy, and I just, started with those questions straight away. Then I moved on to, questions that I find a little bit more easier, and then a little less easier, and then the questions that I find the hardest. Because essentially you're trying to maximize the marks that you can get in the exam. So in terms of preparation as well, the tip that I usually give to all my students is really try to familiarize yourself with the exam structure, and that can happen when you're doing a lot of practice questions, a lot of practice exams, especially for math subjects. Probably not for humanities subjects, but definitely for maths methods and any other math subjects that you might be doing. And also, make your summary book really good that you can, and try to have it done as soon as possible so that when you're doing practice exams, you can use the summary book to your advantage, and make sure your summary book is not, absolutely everything that you have accumulated down here. So your textbook, your notes, every single exam that you've ever done, just make sure it's very concise, or try to make it concise as possible, because that way you'll know exactly where everything is in the exam. But otherwise, thank you and good luck for your exam. I hope you all do the best that you can, and you're all happy with your study score at the end. Thank you everyone for coming to the lecture. See you soon.